In this lesson, we will look at concentration and dilution. We have already investigated concentration in an indirect way, because when we look at concentration, what we're doing is showing exactly how much solute is dissolved in a given amount of solvent. Now, the majority of solutions are in the liquid state where water is the solvent. And so when we're in chemistry and we see the symbol AQ, which means aqueous, it means dissolved in water. So our solutions are mostly going to be water-based solutions. One thing to note is that solution chemistry is actually the most common way to work in the lab. So as you're going to see, we're going to be able to, once we know how to deal with concentration, we're going to be able to do so many more experiments, and you're going to see this unit many, many times from now until the end of your studies of chemistry. The concentration provides us with information about the relative quantities of solute to solvent. And it's always listed as the amount of solute per amount of solution. This is a general form of concentration, and there are many different units that we can use to express concentration. If you look around your medicine cabinet, you'll see some of these ways. So for example, on your toothpaste, you'll see a percent of mass by mass of fluoride in a sample of toothpaste. On a bottle of alcohol or on vinegar, you might see a mass per volume percentage. And when we were looking at solubility curves and we saw the mass of solute per 100 milliliters of water, that was also a form of concentration. Now, as chemists, we need to deal with the mole, because how we relate substances to one another is with the unit of the mole. So we're going to use a special concentration called molarity. And the molarity, which is the chemist's concentration, is expressed in moles of solute per liter of solution. The general formula is C is equal to N over V. It's not uncommon to see the C here replaced with a capital M, so sometimes people refer to it as molarity, M equals N over V. We're going to use C. What's very important to note is that the volume, when you're dealing with molarity, is always going to be in liters. And this is really important to remember, because a lot of the times when you're doing labs in chemistry, you're not going to be dealing with large quantities of solution like liters, you're going to be dealing with milliliters of solution. So it's going to be very routine for you to be converting from milliliters to liters, where you divide by 1,000. Now the units for molarity are varied. So the most basic form is to have the units being moles per liter, which is just using the moles on the numerator per liter in the denominator. Another unit that we can use for molarity is capital M. So you may have heard or seen in places and not really understood, it might say a 0.1 big M solution, or it might say a 0.10 molar solution. The capital M stands for molar. Now it's important for you to be able to switch between these two units and be very comfortable with them and recognize them as concentration units. Another form that you sometimes may see, and you will sometimes see it in textbooks especially because they're trying to save space, is you might see it reported as moles times liters to the -1. This is just moles per liter as a different format. As you know, when you have an exponent of -1, okay, that really is a variable that can be in the denominator. Let's try some practice problems involving our formula. In example 1, we have a solution that has 9 moles of sodium chloride dissolved in exactly 500 milliliters of solution. What is its concentration? So we've got C is equal to N over V. The moles that we have is 9. and our volume here is 0.5 liters. Now, as you're going to see when we start to prepare our own solutions, when you see a value like 500 milliliters of solution, this will be prepared in a special kind of flask. So you can take these as being exact values. In other words, you can take this as having 3 significant digits. So when we finalize our answer here and we find that it's 18, we can report it to 2 significant digits limited by the 9.0. So I can write 18 moles per liter, or I could write 18 molar, or 18 capital M. In example 2, the concentration of a hydrochloric acid solution is 6 molar. How many moles would exist in a 3 liters of the solution? So this simply requires us to rearrange the formula. We want to know the moles this time, so moles is equal to C times V. Our concentration is 6 and our volume is 3, already in liters, so we don't need to do a unit conversion in this case. And we find that we have 18 moles. And again, we've got 2 significant digits. In this next question, we're moving towards being able to prepare a solution of a given concentration. And this is something that I do on a very regular basis to prepare for experiments that students do. If I need a solution that is 3 mole per liter of potassium nitrate in order to do an experiment, and I've determined that based on all the numbers of students, I need 1,500 milliliters of solution, I need to figure out how many grams are required in order to make that solution. So this is going to require me to do 2 steps, and I'm going to use 2 very useful and common formulas. The first thing that I need to do is figure out how many moles are required in order to make this solution. So I want a 3 molar solution, and I need 1,500 milliliters, which is 1.5 liters. And so therefore I need 4.5 moles total. So I know how many moles are required to make the solution, but in order to actually prepare it in the lab, I've got to determine how many grams that is. So I need to use my second very important formula. Moles is equal to mass over molar mass. I rearrange it, so my mass is my moles, which are 4.5, times the molar mass of potassium nitrate, which is 101.11. And what I find is that I need 450 grams. Okay, so again, I would consider this to have 4 significant digits because I'm going to use a specialized flask to do that. So I'm limited to my 2 significant digits, which is why I rounded to 450 grams. In example 4, we've got a solution that's been prepared and we want to identify its concentration. So we've dissolved 0.35 grams and we've made a 65 milliliter solution. So again, this is 2 steps. I need to first figure out how many moles I'm dealing with by calculating using mass divided by molar mass. So I've got 0.35 divided by 169.88, which is the molar mass of the silver nitrate. And I find that I have 0.00206 moles of silver nitrate. And that is dissolved in 65 milliliters of solution. So that means that the moles divided by the volume, and my volume I need to put in liters, which is 0.065, and that gives me 0.032 molar silver nitrate. And so those are the basics of solving problems using the molarity formula. Now what you'll see next in your note is that there are steps to preparing a solution. And we're going to review that, and you're actually going to prepare your own solution for an upcoming lab. What we'll discuss next is how to do a dilution. So in the lab, there are two main ways to make a solution. Sometimes we'll make a solution by taking a solute in its solid form and dissolving it in a certain amount of solution. Or we already might have a solution of a certain concentration, and we might want to use that solution, referred to as a stock solution, in order to prepare a solution of a different concentration. If we're going to use that method, what we're going to be doing is what is called dilution. So we're only going to be able to prepare a solution of lower concentration, and we're going to be diluting it. So we're going to be adding water to a certain amount of that solution in order to prepare our new solution. So let's look at a visual here. We've got this solution here that's got a certain number of moles in a certain volume. And what we've done to prepare this second solution is we've increased the volume of the solution by adding water. If you count, you'll see that the actual number of solute particles in both solutions are exactly the same. But when you think about the concentration formula, C is equal to N over V, if we change the volume, if we increase the volume, that's going to decrease the solution's concentration when we keep the number of solute particles the same. So let's investigate this. Suppose that this solution has a concentration of 5 moles per liter. So it's a 5 molar solution, and the volume of it is 1 liter. And suppose that this solution has a volume of 2 liters. What we've done here is we've taken the moles that are in here and we've put them in a different volume. So we can calculate using moles is equal to the concentration times the volume. And what I'm going to do is use the little subscripts of 1 to represent that this is my solution 1, so my solution before the dilution. The moles that I have in this is equal to 5 because I've got a concentration of 5 and a volume of 1. So I started with 5 moles in this solution. And what I've done is I've transferred the moles into this solution. And so now the concentration in here is equal to the moles in here divided by the new volume. So my new concentration here, I've got the 5 moles, and I'm dividing by 2 liters. So I end up with a concentration of 2.5 molar. Now again, some of you might have seen that right away. If you double the volume, you're going to half the concentration. You're not always going to be working with such nice numbers though, so it's important to understand the concept here and how to work with formulas in order to solve when you have more complicated numbers to deal with. So in this case, we've solved for our new concentration by doing 2 steps. We figured out the moles that we have that are in our new solution, and then we were able to solve for our concentration using our concentration formula, N over V. Now when you're doing dilution, because the moles that you have from your original solution is actually the same as the moles in your final solution, there's actually a quicker formula that can be much more efficient. And it comes from the fact that we know from over here that the number of moles that I have is equal to C1 times V1. So the number of moles in solution 1 is the concentration of solution 1 times the volume of solution 1. In this solution, I can say the same thing. The moles in solution 2 is equal to the concentration of solution 2 times the volume of solution 2. Now, because we are diluting solution 1 to prepare solution 2, and the moles that we had available in solution 1 are the same moles that we have in preparing solution 2, what we know is that the number of moles in solution 1 is equal to the number of moles in solution 2, and therefore, what also must be true is that C1 times V1 must equal C2 times V2. So let's look at the same scenario using this formula instead of doing 2 steps. We knew that our concentration of our solution 1 was 5 mole per liter, and that our volume of solution 1 was 1 liter, and we didn't know our final concentration, but we knew that the volume of the final solution was 2. So when we do this math to find the C2, we're doing 5 times 1 and dividing by 2, and we're left with 2.5 molar. So whether we solve in 2 steps or whether we solve in 1 step using the dilution formula, we get the same concentration of our final solution. Now it's important to understand the concept, but we will use the dilution formula to solve most problems. My biggest piece of advice for solving these problems is to do your best to try to imagine the scenario and try to think about if you were doing this in the lab, what would it look like? So in example 1, we have a solution of sulfuric acid that has a concentration of 2 molar. So this is my starting solution with concentration of 2 molar. And I want to know what volume I would need in order to make a solution that is 0.1 molar and 100 milliliters. So I know my final concentration and my final volume, and I would like to know how much of this solution I will need in order to prepare this. So when we look at this, C1V1 equals C2V2. I'm trying to find how much of this solution I'm going to use in order to prepare this solution. So my V1 is going to be equal to 0.1 times 100 divided by 2.0. And what I find is that my volume is 50. And the units of my volume are milliliters because when I'm using this formula, I used 100 milliliters for my volume. So therefore, the units of this volume are going to milliliters. Now this is very similar to some of the gas formulas that we use where we said it doesn't matter what the units are as long as they match each other. So if you feel like you're going to forget when you're using the C equals N over V that you must use liters, then it might be in your best interest to just always use liters when you're dealing with volume. If you can handle flipping between the two and knowing that here you have a choice as long as they match each other, then go for it. Okay, so let's think about what this means. This means that I need 50 milliliters of this solution. Okay. And then the rest of the 100 milliliters is going to be water. So to prepare this solution, I'll take 50 milliliters of solution A and I'll add water to make it so that I have 100 milliliters of solution. And that is a diluted solution with a concentration of 0.1 molar. Example 2. What is the molarity of a solution prepared by diluting 55 milliliters of 1.25 molar cobalt chloride to 100 milliliters. So basically what I'm doing is I'm taking 55 milliliters of this solution, and then I am adding an extra 45 milliliters of water, and I'm getting a new solution of a diluted concentration. So this is my C1, this is my V1, this is my C2, and my V2. So reading the question and deciding what is your initial concentration, what is your final concentration, what's referring to the starting and the final scenarios is the most challenging part. Okay, and it takes practice in order to get really good at it. And again, trying to imagine it, imagine what the scenario would be in the lab is the best way to get good at it. Okay, so we've got 3 significant digits here, so our molarity is 0.688. And what we're going to be doing is we're going to be doing an experiment where you have an opportunity to make your own solution from a solid, and then you're going to prepare a series of dilutions. So you'll get really good at the skill, and you'll see how the calculations come into play in order to do dilution.